Welcome back, all of you. Our next session is demonstration of ANSI software. Let me introduce the speaker of this session, Dr. Kaushik Sheth. Dr. Kaushik Sheth obtained his MSc degree from IIT Kharagpur in 2018. Then he completed his PhD degree in computational chemistry from Indian Association for the Cultivation of Science in 2024. His research focused on the development of efficient computational method using modern technique like parallelization and machine learning. Over to Kaushik.
Am I audible? Okay. So thank you for the nice introduction. Hello, I am Kaushik. So I am one of the developer of this code. So let me just share my screen. Hmm. Okay. So I will in this session I will show the goal of this code, its inner working, and uh, sooner I conclude with the demonstration. So I hope during the last session you understand what Professor Ghosh tried to say, the scaling issue. People mainly from the computational chemistry background, I think they are able to relate the problem. So I just reiterate the thing that we are trying to solve a large scaling problem. So we are not the machine learning expert, but we have used machine learning to circumvent the problem. So being said, so if this is an interactive session, you can stop me anytime if you want. So don't hesitate. So I just start with session. So this one another things to be mentioned that this project is done with the funding provided by NSM and all the facilities by CDAC and ICS Kolkata. That is my PhD institute. So the main question is what we want to measure with the software. You know the name ANNCI. So we understand this problem with an example. Suppose we want to measure the spin state of a molecule. For this case, consider naphthalene. You all know naphthalene. It's a you can buy it from the grocery store. This is a C10H8 system. What do I mean by C10H8 system? It's 10 carbon and 8 hydrogen. It's make a ring like this, and this each unit we call it a benzene ring. So here two benzene rings is situated near each other and make a naphthalene molecule. This type of system we call it polyaromatic hydrocarbon system. Why hydrocarbon? Because it's only consists with hydrogen and carbon. Polyaromatic mean there is multiple of this benzene ring or make this kind of a molecule. And another thing to be focused to be considered that spin state. So what is spin state? Spin state basically energetic state of a molecule which display various kind of a spin. Each spin state molecular property is changed. So knowing the spin state, we can design a molecule for a particular task. So the general purpose from your graduation level of chemistry, we know that there is a molecular orbital theory where we have a orbital S, P, D, F, that kind of a orbital. This is the atomic orbital, for this is the molecular orbital. And each molecular orbital, we can place the electron. So the electron occupy the orbital and may give us a configuration. If we look at the orbital itself, it's something look like that. So red and blue are the electron finding probability. HOMO means highest occupied molecular orbital. This one LOMO for lowest unoccupied molecular orbital. So for this type of a molecular orbital, we have a configuration 2, 2, 2, 2, 2, 0, 0, 0, 0, 0. What 2 and 0 means? 2 means the orbital is doubly occupied. 0 means or there is no electron occupancy. We for a strongly correlated system where the orbitals are not far apart from each other, we may have one electron here, another electron is here. So this is corresponding configuration 222 11000. So as Devashri Ghosh said, for the 30 pi orbital, the number of configuration is going to 10 to the power 99. So that's the huge problem. Another thing is that molecular orbital calculation itself a costlier calculation. So that's make the competition is unaffordable to perform in any computer present in this world. So finding an efficient method, we use Heisenberg spin-half model Hamiltonian. What is the model Hamiltonian? Model Hamiltonian is a Hamiltonian which captures the essential physics while ignoring the details. This Heisenberg Hamiltonian operator look like that. So it's sum over ij, jij, si, sj with the negative sign. Ij is the site. So suppose we have this kind of a system. We don't know what. So these black are site and the bar between those black circle are called their bond. So these black are called sites. So the site can be an atom, molecule, lattice, anything. So we don't specify anything. So for this kind of a system, a Heisenberg model Hamiltonian can be applied. And Jij is the coupling between the site 1, site 2. We mark each of the site and give a name. But we start our talk with molecule, a naphthalene molecule. How come this Heisenberg spin-half model Hamiltonian can address the problem? So after some engineering, we can show if we ignore all the light atom, that is the hydrogen, we can make this kind of a structure. So this side only have the carbon atom. So and the bond between the carbon atom, the molecular bond, we consider it as a bond. So we can show that these two systems are equivalent. How? So to make that, the Heisenberg Hamiltonian only able to see the nearest neighbor. One only know the existence of 2 and 10, nothing else. 10, the number of 10 side only can see 1, 9 or 5. He has no information about the other. So if we make a bond order file, bond order means which side are make bond with which side. So 1 make a bond with 2, 2 make bond with 3, 3 make bond with 4. Similarly, 9 make bond with 5. 10 make bond or 10 also make 9 also bond with 5, 10 also bond with 5. So for this kind of a system, this for both system the bond order file is same, and in Heisenberg model this is their identity. So for Heisenberg model, the molecule or this kind of a ladder system both are equivalent. So we can use the Heisenberg spin-half model Hamiltonian in this case. So now coming to the SISJ, that is a spin. So if we put up, down, up, down, up, down, up, down, up, down, this is a spin spin operator. This is the spin. So if we put up in the number 1 side, down is number 2, up in number 3, down is number 4. This gives us a configuration 1 0 1 0 1 0 and so on. 1 for the up, 0 for the down configuration. Similarly, if first 3 are up, then down, up, down, up. This is corresponding configuration. So this is for the numerical representation. So in this case, there is also exponential scaling. The scaling may be not as huge as the molecular orbital problem, but our scaling is present here. So though the model Hamiltonian itself computationally cheaper, but we not able to get rid of the exponential scaling problem. For that, we need a selected CI problem. So all the 1 0 1 0 configuration are represented in a circle, and the whole box are called configuration, full configuration space. So for the good thing for us, if we somehow able to measure the importance of each configuration, we get this kind of a graph. X-axis is the magnitude of the CI coefficient, y-axis is occurrence. So we see that the higher in magnitude, CI coefficient means this is configuration and their importance. So if we see the higher in magnitude, that means this part of the graph, the configuration is lesser in number. So if somehow we able to truncate the configuration space, that means we only take the important configurations and somehow able to differentiate between the important and unimportant configuration, we can gain and then apply the Heisenberg Hamiltonian only the important configuration, we can gain much of a computational time. For that purpose, we use Monte Carlo configuration interaction. So this is the heart of our whole algorithm, the Monte Carlo. So what is Monte Carlo? Monte Carlo is a numerical technique that make use of a random number to solve a problem. So here is the same configuration space, but one thing is we don't know which configuration are important, which configuration are unimportant a priori. It is not able, we if unless until we calculate the whole thing, we are not able to get that. For that, we use Monte Carlo. So at first we select some configuration. For this demonstration is only 6. So this is called subspace. Please take the note that this term subspace is going to use for the next part of the demonstration. So please make a note. So we have a subspace. We only consider 6 configuration, build a Hamiltonian matrix, then calculate the energy and CI value from the Hamiltonian diagonalization. From the CI value, we calculate the spin. Spin is a measure we which need to do for the to know the quantum state of a molecule. So from that we updated the configuration space. So we change the subspace and look for the other configuration, and this configuration and previous configuration then compare, and we decide that which of the total configuration are important or not. And this process continue till we reach our final iteration, final optimized space. So this is the whole idea. Now look at the workflow of this code, that is machine learning assisted MCCI protocol. So here we use machine learning to assist the MCCI calculation. So what we do, we at first initialize subspace. So this is denoted as this part of the graph. This red dot a subspace, that means 101010 configuration, means orientation of the spin at each side. Then we label the data, labeling and data accumulation done by diagonalization. Diagonalization important to get the energy. And initially, for calculate a machine learning calculation, you need a repository of data. Without the data, machine learning can't be able to do any calculation. So first few iteration of our calculation is the data generation phase, where machine learning does not kick in, does not take place. So we update the sub-Hilbert space only with the Monte Carlo configuration interaction. Once the data generation phase is over, we go to the machine learning part denoted by the blue square. So sorry. So here at first we learn from the data, then we expand the space using the machine learning information, then we expand or update the subspace configure sub-Hilbert space with the known information provided by machine learning, and final labeling and data accumulation done by diagonalization. And ultimately we check if our energy and spin value are converged or not. If the value is converged, we terminate the calculation. Otherwise, the machine learning process continues. If we look into our code in details for later part for the reference, you can see few model, that is the setup, Heisenberg, Hamiltonian, diagonalization, new generation, CI regulation, and another convergence and spin calculator part. The number 1, 2, 4, 5i, 5, 2, 5, 3, 5.4, 6, all are the corresponding to this algorithm. So for particular part, this module take place. So if you got the time to look into the code in details, you can relate at that time. So now coming to the main part, how one can run from all the theory on the algorithm, how one can run the code in his or her machine to get the result. So for that, our test case is going to be the same, naphthalene, and the state we are targeting is singlet. What is a singlet mean? That is, it has only one representation. Singlet means there is no unpaired electron. So suppose this is a 10 unpaired, not electron, the unpaired spin site. So suppose this is a 10 site system. So for this system, we have 5 up electron, 5 up spin, 5 down spin. So that's make the total. There is no unpaired spin. So there is 5 up, 5 down. So that's called singlet. For triplet state, the reference is coming later in the part. Triplet state, for the triplet state, we have 2 unpaired electron. How a triplet state can be possible for 10 side of system is 4 up spin, 6 down spin. From that, we have 2 unpaired up spin, or if there is 6 down spin, 4 up spin, we have 2 unpaired down spin. That make a system triplet. So please, and each spin have ms value half. So you know the jet component of a spin, that is ms. So for a singlet state, 5 up, 5 down, for this case there is no, so total ms is 0, because plus half for the half for up and minus half for down, so total 0. and total spin expectation value is going to be 0. For in the case of triplet, the ms value is going to be 1 and spin target value is going to be 2, S2 target. And as I discussed earlier, we need a bond order file. So look at the bond order file in details here. So 1 make bond with 2. So the first line. 2 make bond with 3. Second line of the bond order file. 3 make bond with 4. 4 with 5. 5 with 6. 6 with 7. 7 with 8. 8 with 9. 9 with 10. And 10 make bond with 1 and 5 also. So from this character, all the bond are included. Okay. Now get a close look at the input file. What is there in the input file? So we have a fixed pattern to write the input file. At first, we have a header that start setup and end start end setup. So please do not change in this file. Though this is the identifier for the code to know from where the input are started. So if you see in the input file this section of the code, you can see there is two part. One part is before the comma sign, one part is after the comma sign. So before the comma, this is called flag, and the sign after comma, it is called variable. So for this calculation, we use Heisenberg model as our model system. There may be, if you know model Hamiltonian, there means you maybe read Ising model, Heisenberg model, Ghosh-Majumdar model. So for our case, we use Heisenberg model. Number of side you need to specify. Number of side 10 for this case because this is a 10 side system. In your example, my colleague Rahul will show when the example, you see your system side may be changed. Now coming to the subspace part. So if you remember, I show you that a circle. So we are only able to consider 6 configuration in that case, but in real case, our configuration or our space may be larger. For a larger size of system, this subspace size may need to increase. So we start the calculation with 100 subspace size. This is the end state. Please keep it 10 because for our calculation we make it 10. Then we have a parameter called max iteration, that is 15. We only tried to run the 15 iteration for this calculation. And there is energy tolerance value or spin tolerance value. Before the max iteration reach, if our system are reach this tolerance value, this threshold value for spin and energy, the calculation will be terminated here. There is another thing is J value and beta. This is corresponding to the coupling strength between the two sides. And another main thing you have to note, this is a bond order file. So bond order, this is the file bond order 10 ph10.dat. So in that file, you need to put all the bond order details. And then there is a restart false because we are not going to restart the calculation. So this is the input structure. After you completely run the calculation, how we are going to run, Rahul will show you in the hands-on session. But you got this mainly these 6 output file, and please have a look on the output file, what are given in this output file. So for that, I am going to log into the cluster. Please bear with me. I just show you in the next part. You will do that hands-on in your own computer. Rahul, is my tab visible?
Yes.
Do I make the font large?
It's fine.
Okay. So focus in that part. So there is, so first column, so there is total 8 to 10 file. So this is our input file as I show you. Okay. So this is input file, same as shown in the PowerPoint presentation. And if please note that there is a file bond order hyphen ph10.dat. So the same file is also need to be present in the same directory. So bond order. So this is the same file. 1 make bond with 2, 2 with 3, the same thing. 10 with 5 and 5 with 10. After the successfully completion of the job, you have the main output file, which is written the same as input name, and after that there is a .out extension. So if we look at that file, okay, first section is only the input part. After that, we have a this calculation write some output. So what is the parameter? Let's check it quickly. So first thing is the iteration. So we run 1 to 15 iteration. So the first is the flag for the iteration identifier, then is the space. So we started with 120 configuration, and we see with the increase of the iteration that subspace size is increased. This is the energy. So we also see the energy of the system getting lower. That's mean we are in the right direction. Any kind of optimization, if we getting the lower energy of a molecular system, that's mean we are going to the stable state. And if we look at the final parameter, that is the spin square expectation value, it started from 2 getting to 0. That means we are reaching toward the singlet state. For the singlet state, spin expectation value should be 0. And after the 5, all the iteration, there is a summary of the 10 states. So we have 10 spin state 1 to 10. There is energy value corresponding to state, and we also have the spin expectation value. So first state can be, we can call is the singlet, second state is the triplet, and so on. So from the differentiate of the energy, we can also have the idea of a singlet triplet energy gap of this molecule. So this is the main output. Okay. So there is also another output. So let's quickly look at the PPT. So one thing is the input. So dot out dot basis, the second input file, that is dot out dot basis. So here is all the configuration, up, down, spin orientation, which are important for the system, is given in that file after final iteration. Similarly, their importance are also given in dot out dot ci file. So the first is the so please please keep it note that the important square are important. So the absolute, so this value are considered as a absolute. So the first configuration is most important because its value is higher. Then the importance of this configuration getting lowered with as we progress in the file. Okay. And there is also another. Okay. There is also another thing is the input file dot out dot model dot path. The neural network we optimize during the calculation are saved in that file. If we want to look in for the further calculation, if we want to restart of our job, our saved neural network model are in that file. And there is also an error file, and we have also a subspace file where all the subspace training subspace are given. So I'm not going into the details for this part. Just I want to quickly show how to if we visualize those data, what we can able to see. So for that, I just move to another file because for that, okay, give me a second. Don't try to follow anything right till this point because Rahul will show the exact step how to do all the thing. So if you visualize those data, first one for the energy, as we see for another calculation, we run it for the nearly 30 iteration. The energy is started from 2.5 EV, and it's with the iteration, the value is lower. And as we see, as the data iteration progress, there is not as much improvement in the energy. So for that, we can see the result are in the plateau. So from that, we can see okay, our system are getting in the stable state. So this is the first data. So similarly, if we try to look at the spin value. Okay. So similar thing you can see our target spin is 0 for the singlet. So initially we have a higher spin state, and with iteration, the value are getting lowered, and after few iteration, it's nearly reached to 0. So we can say that our spin is purely a singlet state. Similarly, we can have the machine learning result, the actual versus predicted. Okay. So this is not a proper representation because for machine learning to work, we need sufficient significant larger system and sufficient of data for the this iteration. We can see there is some trend with the actual and predicted data. So we can see our machine learning kick in, but we are not sure about its accuracy till this point. And for talking about the accuracy, we can also have to look their exact value, the train and test error. Okay, I messed up with some. So okay, Rahul will show during his presentation all the graph. So this is the basic idea to visualize those results and get the output of those results. And take back to the presentation. So this is so another thing, if you want to run this code on your machine, you need some prerequisite. CUDA device means GPU system. When the driver, you need a Python, PyTorch, and Numba libraries, and F2 Py3 system. You need to git clone the code from the GitHub. Rahul will quickly paste this in the chat box. You will follow it later. Don't need to hurry up. And our code also use the Fortran code, because sometimes Fortran is much faster than most of the time Fortran is much faster than Python for any unit of computation. So a large part of computation we have a Fortran. So F2 Py3 that to change the Fortran to Python, and then we move to that code for a particular name to run, because sometimes there is F2 Py3 has different version, so we have some different name, so we need to change that. And for a better idea, please go to the GitHub page. I just quickly show you. So this is our GitHub page. In the GitHub page, you will find all the details, including I mentioned in the PPT. So this is all the repository where you have a description what the code do, the prerequisite, the installation, and the talking about the input, how we can create the bond order file, how to run the code in your machine, what the all output is and what all output do. And you also get same page a research article. This is the scientific research article published for this work. So if you have the access of the journal, you please have a look and get a view what the coach in its entirety try to achieve. So for that, and another thing is that all the parameter in the hands-on session we are going to tell you that all the parameter has a science behind that. So for that, you please how to please pardon me, I just figure out something. Okay, in the same research article you will get a supporting information. For that supporting information section, all the parameter used or changed in the code are given in page number S2. From that you can able to change the parameter, and the logic behind the parameter is given in the main article. So this is from my side, and this is all from my side. I think I will paste the link of the GitHub page. From that you will have an idea. And now the key contributor is the code, or the all the software is Professor Ghosh, because it is originally her idea and we are work on that. Kaushik said that's me. I mainly develop the code, and two of our lab senior or my collaborators Sumanto and Madhumita, they are also part of this work. And Mrs. Nisa Agarwal and Rahul from the CDEC, they are also developing to make the code parallel. Though this workshop is on in the serial version, but we are going to upload a parallel version very soon. So this is all from my side. If you have any question, please let me know. And otherwise, Rahul will proceed with the further part of this talk.